Hello dear professor, hello everyone. Today I'm gonna answer chapter 5 GeoGebra activity. Question number 1. Since high school, for me the equal sign has always meant that the right side is equal to the left side. As many apples on the right side as there are on the left. No more, no less. Question number 2. These examples present equality as a process of calculating an answer rather than a relationship between numbers. Students may perceive the sign equal um, as, as, as to find the result, but which is incorrect. We need to show students relationship between one side and another side. Question number 3. Um, it means to determine values that make the equation true. In simple way, it's a number that will create a balance of expressions. Question number 4. Now we need to go through the website and look at our equation. Let's go through this link. Let's make our own. For example, x plus 3 plus 7. So I started with the equation x plus 3 equals 7 on the balance scale. To generate new equivalent equation, I applied the properties of equality. What does it mean? So if you put on the left side 3 tiles and on the right side also 3 tiles, thanks to this side we can see the balance. But this is not a solution. What do we need to do? Here we can see x plus 3. 1, 2, 3. On the right side 7. So this keeps the equation balanced because subscribing or the same value from both sides maintains equality. The math playground applied visually ensures the equation remains balanced. When I add or remove tiles from one side, I must do the same on the other side to keep the balance equal. The applet provides feedback by making the equation correct when it remains balanced. And we can also see the green sign that everything is correct. Let's go through our next question. Question number 5. We need to press the icon with 2x. We will create a two-step equation. So we can see the equation 5x plus 2 equals 7. Let's solve using the balance scale. What do we need to do? Here is 5x plus 2. 5x plus 2. And on the right side, 7. So we can see our green sign, so which means everything is correct. The math playground applet confirms correctness with a green sign. What's our final explanation? This applet check the balances with a green check mark when equation is balanced. Each operation performed, subtracting or dividing, is reflected visually, reinforcing the concept of equality. Let's answer our next question. Question number 6. How does the applet handle the division property of equality? The applet divides tiles into equal groups on both sides. This helps students understand that dividing both sides of an equation by the same number keeps it balanced. However, it may be difficult to apply this fraction and negative numbers. Question number 7. Balance scales show that both sides of an equation must remain equal. This helps students visually see how addition, subtraction, multiplication work an equation. Question number 8. What are limitations of the applets? It doesn't always work with functions or complex equations. Students might rely too much on visual and struggle with solving equations without them. It is best to use the applet as a supporting tool, not the main teaching method. Question number 9. So now we need to go through GeoGebra spread. GeoGebra. So what do we have? We have two membership options. First, individual membership costs $25 per year, and executive membership costs $50 per year but provides 2% cashback on all purchases. We need to determine at what annual spending amount the executive membership becomes more cost-effective than individual membership. Let's set up the equation. Let X represent the amount spent annually at the Warehouse Club. The total cost equation for each membership. So let's make equation right here. Int guess. Let's open guess. Enter the equation. So let's press enter and see the answer. X equals 1250. Let's impute both functions in the graphic view. So here it is. And now we need use the intersection tool. We use intersection tool. We can see here our intersection, which means if you spend more than 1,250 per year, the executive membership is a better option due to cashback savings. So let's go to Canvas and look our next question. Let's go in. So in GeoGebra, editing a vertical line at x equals 1,250 confirms the break-even point is consistent across different representations. This happens because equivalent transformations maintain the x-value in algebraic manipulation. Changing the scale in GeoGebra ensures that both lines align properly. So now we need to continue to apply properties of equality and analyzing the graphical representation. So let's enable spreadsheets. And guys view. In cell A1, enter the left side 25. In cell B1, enter the right side of equation. If I'm not wrong, it was 50 minus. So now we will step by step simplify the equation in CAS by performing operation on both sides. We will subtract 50 from both sides. A1 minus 50. A1 minus oh, A2 to right, and the other side also A2 to right. This simplifies equation to x equals 1250. Now we see the solution x equals 1250 remains unchanged. Let's see graphical analysis. We will add the intersection point to the graph. Go to graphic view and enter two equations. It equals 25 and the second one equals 50 minus. And now let's use our intersect tool. And select both graphs. GeoGebra will display the intersection point 1250. We can add again a vertical line through. To ensure that the line intersects both graphs at the same point. Here you could see. And now we are ensured that the line intersects both graphs at the same point. Each property of equality applied, subtraction or division, doesn't change the solution, but simply rewrite the equation. The graph confirms the solution, the intersection points remain the same. And the vertical line at 1250 shows that all equation representations lead to the same solution. Let's go to the question 12. Now we need to open GeoGebra, cast view, and enter the equation. So x minus 6. If we press enter, GeoGebra will return Let's type again. X minus 6. After press enter, GeoGebra returned x equals 9. Let's verify graphically. In graphic view, we will enter grep equals x minus 6 and grep equals. So we can see here our two equations, and let's use intersect tool to find the intersection point. Put it here. The valid intersection is, we can see for x is 9 and for y we could see it's 3. The valid intersection is 9 and 3. So the case operation correctly solved this equation and identified x equals 9 as the only solution. Our graphing confirms the solution by showing the intersection x equals 9. This method ensures both algebraic and graphical verification of the solution. Question number 3. Again, let's open our GeoGebra Classic and enable spreadsheet view and graphic view. So in this question, we analyze how changes in the spreadsheet dynamically affect the graphic view and expressions. Let's include x values. For example, 2, 3, 4. And this will be enough. Let's dig in our task. In column B will be shown y values for x minus 6. So let's drag down. Fill the column for all x values. And column C, it will be y values for the root of x. Let's then drag down to fill the column for all x values. So what we're supposed to do is highlight column B and change the color. And now let's click on any cell in column A, then observe how the corresponding points change in the graph view. So let's repeat this for column C and observe changes. So now we need to observe the graph in the graph views. This is our graphic view for our column. The linear function u equals x minus 6 produces a straight line. The square root of function the square root of function produces a curved shape only for non-negative x values. You can see. As we scroll down the spreadsheet, the points move dynamically, showing how each function behaves. Why does it happen? The spreadsheet is linked to the graph, meaning any updates in the table reflect immediately in the plot. This allows students to see and understand how equations behave dynamically. What do we see in the graphic views? Two different graphs appear. Y equals x minus 6, a straight line, and y equals the root of x, a curved function. The intersection point represents the solution to x minus 6 equals the root of x. Question 40. Question 40. Now we solve the equation algebraically in the CAS view. Let's open CAS view. And enter the equation in CAS. So x minus 6 so as we press, the algebra returns as x equals 9. Understanding the differences between CAS and spreadsheet. The CAS method finds all possible solutions algebraically. S equals 9 and the spreadsheet method visualize values, making it easier to interpret the function's behavior graphically. Let's check in graphically. Let's enter. And using intersect tool, we will see only the correct answer is 9. And why does the CAS view show an exact solution? We'll see here that we will see here our solution x equals 9, which means the first method and the second method are the same, but sometimes I notice that CAS show an extra solution, potential extraneous solution, and that's why it's difficult to answer this question, but the spreadsheet plus graphing approach helps confirm which solution are correct. For me, the best way is to use the first method and the second method as well. To question 60, 17, 18, 19, 20, I will answer it in the word format. Question number 21st. GeoGebra's spreadsheet view is a powerful tool for analyzing equations numerically. There are a lot of advantages of spreadsheet view. First, dynamic linking to graphic view. When numbers change in table, the graph updates instantly. This helps visualize how equations behave. When numbers change in the table, the graph updates instantly. I said before. And pattern recognition. By imputing values, students observe trends. Example: for x minus 6 equals x of the root of x, student can see at which x values both sides are equal. The third advantage is support checking and verification. Even if CAS solve an equation, the spreadsheet confirms which values make it true. And also useful for step-by-step explanation. And question 24. Using GeoGebra, finding the number of tiles around the pool. In this step-by-step guide, we will use GeoGebra to visually represent the problem and develop an algebraic expression for the numbers of tiles from the pool. So, we need graphic view. And we need to activate the grid to make alignment easier. Grid is already activated. So let's draw the square pool. We need to select the polygon tool. And we need to use the polygon tool again to create a larger square representing the pool plus tile frame. The new square should have length of n plus 2. So now we could calculate our tile area. View into algebra. Expand. And 2. So what we did, we calculated the number of tiles using CAS in GeoGebra, entered formulas for total area, for pool area, and then compute the difference. Compute the difference. Substituting if n equals 5, we could see that the answer 24. So the correct answer is 24 tiles. We can also change colors. Question number 29. We need to solve 6 different expressions. And then question 30. Question 30 requires three different expressions. No physical model. Plus 3.